so Alex comes to us from Oregon, was taking organic, took advanced organic and said, I want a challenge. And I said, great, go find one because I'm busy. Well, and we, usually when faculty direct these projects, it's very much like, well, here's what I like, and you can pick one of these things that I like. And Alex really wanted to kind of do what he liked, and we sort of came to somewhere in the middle, and I think it turned out into a pretty neat little project. And so I think he did a really nice job of reading the literature, solving these problems as they come up. You'll hear about lots of problems. Some problems went unsolved because, time is finite and the world is mysterious, right? So that's okay. And we're going to hear some cool stuff. So, Alex.
Alrighty. So, I remember it a little bit different from what Deborah says. I walked into his office and I was like, hey, slammed down a little thing and said, hey, Deborah, I want to make stuff like this. And he's like, no, narrow it down.
And also I said, don't call me Deborah, use this like, okay.
Okay, Deborah, whatever you say. So ultimately, after some back and forth between the two of us, we landed on the synthesis of heterocyclic fluorescent liquid crystals. I just said a lot of words in a row, and I promise you that I am going to explain all of them. So, when we break it down, there's 3 parts. Heterocyclic just means that there's multiple different cycles, which is pretty easy in of itself. But fluorescence and liquid crystals are a little bit more finicky. So first, let's take a quick look at fluorescence. So, there are a lot of different uses for fluorescence, all of which you have interacted with on a daily basis, I promise. So if we look over here, we can see that fluorescent lights and Sharpies even use fluorescence to help give them that glow. For fluorescent lights, they emit a broad spectrum to give us the white light, whereas Sharpies are specifically designed to absorb and emit at specific wavelengths to give them that yellow, that blue, that pink glow that you know and love. However, fluorescence is also used a lot in different sorts of technologies, again, for that same impact of giving it a brighter pop to the colors. However, fluorescence isn't just useful for making things look pretty, like with art, which, to be honest, I love fluorescent art. It just looks gorgeous. But you can actually use it in biological systems as helpful markers to, say, track proteins as they go through and perform their functions, or enzymes as they break things down, so that you can figure out at what point the active site is, or even just in a broader sense to mark cells so that you can track them through media. So, now that we know what it does, how does it do it? So the basics of fluorescence are that we absorb a photon, and a little bit later we emit a photon. However, the emitted photon has to be of a slightly different wavelength. And the way that this works is that when a molecule absorbs a photon, it is absorbed by an electron, boosting it from a ground state into some excited state. Now, when we get to this excited state, the electron wants to return to, at the very least, a lower state, but preferably down to the ground state. Now you could think, oh, if we absorb a photon here and pop up to here, we could, in theory, just re-emit that photon right back out and return to our ground state. And yeah, that does happen, but that's not fluorescence. Fluorescence is when we actually lose a little bit of energy through non-radiative transitions before we re-emit our photon. And if you want to conceptualize this a little bit, what that means is that some of the energy from the photon may be lost as heat to the molecule, or put into different vibrational modes or bending modes from the chemical's movement. After we have lost a little bit of that energy through non-radiative transitions, then we can emit a photon again. And that is where our fluorescence comes from, because the wavelength of these two photons is noticeably different. So, what sort of compounds can be fluorescent? And here I've just marked a couple of them up so that we can try to look at them and say, what sort of characteristics do they have that we can stitch together to make a new chemical that I theoretically would go to synthesize. So if we step back and just look at this for a little bit, we can see that there are a lot of these benzene rings stretched through here, which are all connected to each other in an extended pi structure. You can see that here and here as well. But not only are there extended pi structures with just carbons, you can see that there are oftentimes oxygens participating as well. And that can help with the electronic structure to give it extra modes to vibrate, allowing for a greater chance of fluorescence. Okay, so that's all fine and dandy. Off we go to liquid crystals. Now, liquid crystals you interact with on a daily basis. You may not know it, but you do. Liquid crystals are found everywhere in electronics, whether it be on the screen of your LCD TV or the liquid crystal displays that you may have in your calculators and such, but they can also be used in smaller electronic components as switches or detectors for various materials, heats, electricity, magnetic fields, etc. Depending on the properties of a liquid crystal, you can apply it in several different methods. It can also be, liquid crystal or chemicals that contain liquid crystal properties can actually also be used to create stress and heat maps, which can be used in industrial settings for discovering if there's a flaw in a pipe or a heat leak somewhere along a system. Now, I want you to really quickly just try to figure out how a liquid crystal works, because it may seem a little bit odd. Is it a liquid or is it a crystal? And the answer is yes, of course. So what really is a liquid and what really is a crystal? For that, we have to look at the molecular level. So if you think about your stereotypical three states of matter, we've got our gases in which the molecules are all completely volatile and just slide past each other without hardly hitting each other at all. Liquids, on the other hand, there is still that free-flowing ability where the molecules can slide past each other, but they are all still within contact of each other. In a solid, all the molecules are locked into a place but are still able to vibrate. Now, special to solids are crystals, which are basically perfectly ordered sets of atoms or molecules. And what this results in is a perfectly rigid crystal, which of course is part of its name, that is just ordered and allows for for different types of light refraction, or if it's a metallic crystal, electronic conduction. So then, where does the liquid crystal part of it come in? Well, if you want to picture a liquid and a crystal, just kind of smash it right in the middle there. What it is its order, but you still are able to flow between regions of order. So if you look at this, or these couple of pictures of liquid crystal molecular structures, you can see that within sections we have a large amount of order where each of the molecules will all be lined up in the same plane, or in sheets, as in this side here. However, this is still within a liquid system, meaning that the molecules aren't locked into these regions, they just like being there. So a molecule can easily flow through the system. And that is basically how a liquid crystal functions. If you're holding some in your hand, it is a liquid, but on the molecular level, there is a small amount of order. Now, another thing that is incredibly important for liquid crystals is that you use it in soap. even, or in your digestive tract to help sequester things. So for example, one thing that you can do to create liquid crystals are if you use molecules that have both hydrophilic groups and hydrophobic groups, they can actually arrange themselves into these little spheres called micelles. And at its strictest definition, this is a liquid crystal, because it is a region of order within a liquid wherein you can still have mobility into and out of the system. And this is how soap works, and this is also how your digestive bile and stuff help to digest things. Now, a couple of things that we can use to look at liquid crystals are one, polarized light microscopy, and two, DSC, which I'll get to in a sec. So, liquid crystals, because they have those regions of order, actually twist light that go through them in very subtle ways. And if we look at that through polarized light microscopy, we can actually get some really pretty pictures like these two shown here. But how does that work? So first of all, polarized light microscopy works by taking a light source and forcibly polarizing it so that only a single phase of light is going through your sample. Then what happens is when it hits your sample, it will actually twist the light slightly over or different ways in different regions of the sample, which when it hits your analyzer will actually refract into different sorts of colors, resulting in these different pictures here. And depending on the color, you can actually work out how far the light is twisted and the refractive indices that means the liquid crystal has. Now, another thing that we can use to check out liquid crystals is differential scanning calorimetry, like I said. Basically, what this tells us is how chemicals respond to heat and what sorts of phases they have. Liquid crystals are not actually limited to one phase. They can have several different liquid crystal phases, and that is based off of the way that they are ordering themselves within a sample. So by using differential scanning or DSC, we can actually figure out where all of these melting points are. And this can actually be incredibly helpful if we want to use our liquid crystals as, say, switches that are temperature sensitive, or for that industrial application, we can use it to determine where different parts of stress or heat leakage occur. So now we're going to bring it back to the synthesis side of things. Let's take a quick look at some characteristic liquid crystals. If we pause, we can say, well, here we've got a lot of similar stuff from our fluorescent compounds. We've got those benzene rings and extended pi structures. But that's not the important part. The important part to look for of what makes these liquid crystals are these tails on the end. They help to break up the crystallization structure of these chemicals, helping them to attain that liquid crystal state. Alright, so now we've got fluorescence, and we've got liquid crystals. We need tails, we need extended pi structures. So, the chemical that I decided ultimately to make was this. We've got our extended pi structure going through here, and we've got a couple subunits that are pretty well studied. In fact, this section right here in the middle, which is called an oxidiazole ring, is actually very well studied in liquid crystal design. So implementing it here shouldn't be that much of a problem, and in fact would help to expand the literature's exploration. Now, if we look real quick here, we've got R groups on the ends. That is where our tails are going to be going to help this become a liquid crystal. And the reason that I left it as R is that I wanted to exchange different types of tails. Like if you remember here, this tail is kind of branching, whereas these are both perfectly straight. I wanted to try to experiment with some of those to see which one would help to achieve the best liquid crystal phases. So, got our target molecule. How do we get there? So we're going to look at this by a method called retrosynthesis, which is basically you take your final molecule and you cut pieces of it off until you get to somewhere that you can either buy the chemicals or you know how to quickly get there. So we've got our starting molecule. If we look at this, there are several units that, again, we easily know how to get to. This is a triazole ring, which is very easily obtained through click reaction chemistry. And this oxidiazole, again, has been studied throughout the literature, so can be constructed fairly easily. But where do we want to cut first? I say that we should cut right here first to give us this. And this, again, is that click reaction. These azids are very easy to make, so perfect. We don't have to look at them anymore. But if we want to break this down a little bit, we can find that we can cut along these and get back to this step. This step progression is called the Sonogashira reaction, which we'll come back to again a little bit later. And where do we want to cut from here? Well, now we're going to want to look at breaking apart that oxidiazole ring into a hydrazid, and the hydrazid we can quickly get from 2 carboxylic acids and hydrazine. All right, so now I had to actually go and make it. So for our first step, I took some of that carboxylic acid and treated it with oxalochloride. The reason that I did this is because the carboxylic acid isn't actually quite reactive enough to latch on to the hydrazine right away. But once I introduced the acid chloride to the hydrazine, it immediately formed this and promptly gummed up the flask because it formed so quickly that it just flash precipitated out of solution. So this was possibly the single easiest thing that I did in this entire reaction synthesis. It does not get better from here, it only gets worse. As evidenced by this. Closing the oxidiazole ring. I mentioned that it was well studied in the literature, right? Problem is that no one actually says very well how they made it. A lot of the papers that I looked at continuously referenced some random patent from the 50s that I just could not for the life of me find. I tried Google Scholar, I tried looking up through the patent registries, and I just couldn't find this patent for some reason. So eventually what I had to do is I had to call up my sister who works at a library in Canada and ask her to go through physical records to try to find this patent, which eventually she did, so she just snapped a picture and sent it to me. Unfortunately, that ended up being a bit of a dead end because the way that that patent proposed doing it was by baking the hydrazid in PPA, or polyphosphoric acid. A couple problems with this. First of all, we didn't actually have any of that here at Lawrence when I was trying to do this reaction. And another thing is that polyphosphoric acid is not exactly the greatest stuff to work with. Very thick, very corrosive. So I kept digging to try to find some other ways to do this. One of the other ways I discovered was just cook it in dry sulfuric acid. Well, that has pretty much the same problems as polyphosphoric acid. Corrosive, not very fun to work with at all. So ultimately, finally, I discovered that if we use tosyl chloride or mesyl chloride and just stir it over a weekend, it will manage to close this oxidiazole ring. So naturally, I ended up going with the much less corrosive option. So hooray, we've gotten our oxidiazole ring closed, 2 steps down. So next up, we went to our lovely, lovely Soto-Gashira reaction. So what happens here is through some palladium catalysts, we take a trimethylsiloacetylene and replace the bromines on either side of this molecule to give us a chemical like this. However, you'll notice that the silicon group is actually gone. That's because after we perform this reaction, we deprotect it. Now, if you're wondering, why don't we just take this and put that in solution? Well, that's because acetylene itself is a gas and very, very flammable, and so not exactly the safest option to work with, in addition to the fact that it can actually add on both sides, which could just end up polymerizing the entire sample. So by adding this silicon group, performing the Sonogashira, and then taking it off afterwards, we're left just with this instead of some sort of polymerized alternative. Now, this is also one of those really well-studied reactions. Unfortunately, it's not, or it doesn't always work for several reasons. First of which is that the palladium catalyst, there are several different options to use, and depending on what system you put them into, what solvents you use, and how long you want to spin it for, different things may or may not work. So just a couple of discoveries that I made are that you need to actually make sure that your catalyst is still good. The first catalyst that I tried to work with was just the dregs of this little bottle that had probably been opened a long time ago, and unbeknownst to me at the time, it was pretty much entirely oxidized, so it didn't work. The reaction never progressed. So ultimately, when I got my hands on one that did work, I was able to successfully complete the reaction. Now, some other things that are important to do this are that the system has to be completely oxygen-free. And it's, again, to prevent that oxidation of the palladium catalyst. Once it oxidizes, it won't work. And another thing is that triethylamine is the solvent that I have found to work the best. One of the reasons for this, of course, is that triethylamine helps to stabilize a lot of these metallic intermediates, including keeping copper, which is a co-catalyst in this reaction, in its copper 1 state. All right, so success. We've gotten through our Sonogashira. Now comes the step that I never got to work. Yay! Here we have the click reaction. Well studied. Very easy to get to work, right? Yeah, sure, that. So basically what we're doing here is we're taking a group with an azide on it and introducing it with a copper catalyst to our acetyl group. What this does is it rearranges the electrons into a beautiful, perfectly fully conjugated aromatic ring. And this is a very, very fast reaction. It should happen in as little as minutes. However, it never actually did that for me. So a lot of these discoveries are mostly from literature digging. So first of all, solvent doesn't matter. It pretty much genuinely does not matter what solvent you use. You can use water, you can use any sorts of alcohols, you can use just whatever works, ethers and all that. And even aside from that, your copper source can be pretty much anything. Some people clip bits of wire and throw it into the solution, introduce an electric current, and it goes just fine. Other people put some copper sulfate in solution and reduce it in situ with some ascorbic acid, and it goes just great. However, the issue comes if your azide isn't good anymore, like our jar of azide, which was from the 60s, which had probably gone bad at some point. So this of course is just my personal theory as to what went wrong. And there are a couple other things that it could be, but this is my best guess as of right now, that the sodium azide was a little too old for our uses. But I actually did get something to work. So if you look at this, this is some of the samples that I had as shown under UV light. You can see that it's actually fluorescing beautifully. We've got some yellow, or we've got a little chunk of yellow up here, some deep bluish, and some greens around here. Problem is that there shouldn't be multiple colors. There should only be one, or maybe shades of one color. So I needed to purify this. Unfortunately, I got a few too many things out of it. So you can see that I got a pretty pearlescent powder, some sort of yellowish orange, a greenish powder, and a reddish powder that looked almost like rust. So the question is, which one of these is my product? The answer is none of them, sadly. As Frankly knows well. So how do we even know that none of them are actually my product? For that, we use our best friend. This is a picture of our NMR downstairs. And this tells me just how many times I failed. So the NMR, basically what it does is it allows us to look at molecules directly to figure out how they tick and what they are. And to do this, what we do is we can select from a short list of atoms to specifically look for, and it will tell us what sort of situation those atoms are in, whether that be by chemical shift or by integration, telling us how many there are, etc. And once we take all of these different facts and combine them together, we can very accurately draw up what our chemical looks like. So if you want to just take a brief glance at this example, you can see that there is a single hydrogen on this oxygen, and that if we were to integrate this peak, it would tell us there is one hydrogen. Now, why does this have 4 different peaks? That's because this hydrogen is actually being interfered with by these 3 on this carbon, which means that instead of 1 peak, it gets split several times into 4. Conversely, if we look at the 3 hydrogens on the carbon, they're all perfectly identical to each other by symmetry, which means that they will all appear as just 1 peak. But they are being interfered with by that hydrogen on the oxygen, giving us not 1, but 2 peaks, which would be integrated to show 3 hydrogens. And if you extrapolate from this, we can take it to some larger molecules to figure out what they are. So, just as a quick reminder, this is what I was ultimately looking for my chemical. And this is a idealized computer-generated NMR of what it should look like. That isn't quite what I got, though. What I got was something more like this. And just so you're aware, you can ignore these 2 larger peaks right there. Those are solvents that got in interfering with the signal a little bit. So if you step back and just look at this a little bit, you can see that it's almost close. Like if you look over here, we've got these 2 peaks, and they're, pretty close to where they should be. And here, though, things start getting a little weird. There's a very short peak, and it's a little too high from where it should be. And over here, these 3 peaks are all just completely in the wrong spot. But what happens if you look a little closer is that the integration values don't actually line up. These over here are double the value that they should be, which means that either one of these tails didn't get added on, or something else a little bit different happened. So currently, the guess as to what my best product was is actually this. So you'll notice that it fits the NMR from previously because we have half as many tails as we should. But you'll see, we did get some success, right? This cycle happened here and on the other side, and that's good. But what happened that went wrong is right here in the middle. This is what we call Glaser coupling, where because of the copper in the solution from the click reaction, there's actually a chance that two of the triple bonds can cross-couple with each other. Unfortunately, I don't actually know how to prevent this from happening. And sadly, the sands of time got a little bit too far away from me, so this is the ultimate place where I had to stop. Yeah. So, I made something, just not quite what I wanted. Okay, so just a couple quick thanks and acknowledgements. I would like to acknowledge everyone's favorite, the great and powerful one and only Stefan Devert, for putting up with my everything day after day. I'd love to thank DMART for giving me chemicals with weird faces, and Lawrence University for the lab space that I got to work with, as well as Dave Hall and the senior seminar people for listening to this talk too many times and giving me suggestions on how to make it a little bit better. So thanks.
I apologize for people watching at home. I have to see this vicious beast. So, Alex would be happy to answer any questions.
Yeah.
Was there any use for your theorized crystal that you thought your crystal would be better for than the crystals out there right now?
So the short answer is I'm not sure. A lot of that depends on the exact properties that it displays. So you would have to more make it before you can actually figure out which use it would be most applied for.
So to follow up on Sam's question, does that mean that there's not a great way of predicting the properties from the structure?
At the very least, I don't know how to.
Fair enough.
Can you go back to the slide where you had your raccoon slide?
This one?
Thanks.
I can add the raccoon paw back if you want.
I have no further questions at this point. So, in your reading about the click reaction, did you ever see any reactions on terminal alkynes like that? Or, I'm sorry, not terminal alkynes, the internal alkynes. Right? Is there any possibility that some of the other products could have been done, things where the click happened in the middle of that line?
So I didn't actually look into that. The other thing is that I don't even know 100% if the click reaction truly worked or if something else totally weird happened.
I mean, we don't know like 20%.
So for that, the LCMS would help a lot if it was up and running.
Well, and again, the Glaser coupling is copper and oxygen. So keeping the system oxygen free should mitigate that.
Although, from all of the literature that I could find, it never indicated that the click reaction should be kept oxygen free. So, I mean, it's used in biological systems all the time, so. Anyone else?
All right, let's think of something here again.